Welcome to this tutorial, where we solve a practical case study for an overloaded 33/11 kV substation feeder. In this example, we'll calculate the reactive power, capacitor bank size, current reduction, and system loss reduction. Let's dive right in based on real scenario. We have a problem in 33/11 kV substation where a feeder observed an overloading of 210 ampere, poor power factor of 0.75, poor voltage regulation, conductor broken at many places at different time. Please pause this video and read this question. Now we have to find required capacitor compensation to improve the poor power factor to 0.95, current reduction in feeder and corresponding reduction in losses. Let's start. Step 1, System Details and Active Power Calculation. We start with the given system parameters. The voltage is 11 kV. The feeder current is 210 amperes. The initial power factor is 0.75 lagging. This power factor is recorded during overloading, and we aim to improve it to 0.95 lagging. These are the parameters we have in an actual scenario. First, we calculate the active power using the formula. For a three-phase system, active power equals square root of 3, multiplied by voltage, current, and the power factor. Substituting the values, we get P equals 1.732 multiplied by 11, kV multiplied by 210 amperes and 0.75. The result is approximately 3.002 megawatts. Now move on to the next step. Next, let's find the reactive power required for compensation. The formula for reactive power required is active power P multiplied by the tan phi, initial, minus tan phi, final. Substituting the value. 3 times tan cos inverse initial power factor minus tan cos inverse of final power factor. Now solving the equation, we will get the value of capacitor bank required. The final value comes after solving the equation. Q is equal to 1.683 MVAR or 1683 kVAR. Hence, 1683 kVAR capacity of capacitor bank required to install and connect in the 11 kV bus bar to improve the PF to equals 0.95 lag. This is the size of the capacitor bank needed. Now move ahead. To find the current reduction before and after compensation, we find out the apparent power in the system. The initial apparent power is square root of 3 multiplied by voltage and the feeder current. Substituting the values, and after solving we got 4.004 MVA. The final apparent power is active power divided by the target power factor. Here also substituting values, S equals 3 megawatts divided by 0.95, which results in 3.160 MVA. Using these values, we calculate the final current with the formula. Apparent power divided by square root of 3 times voltage. Substituting the values, the final current is approximately 165.7 amperes. The reduction in current is initial minus final current as per formula. This gives up 44.3 amperes. Hence, 44.30 amp current has been reduced after 1683 kVAR capacitor bank installed in 11 kV bus. Great. This is also shown in graph, where current has been reduced significantly. Lastly, let's estimate the reduction in system losses. We know losses are proportional to the square of the current. The initial losses are proportional to 210 squared, or 44,100. The final losses are proportional to 165.7 squared, which equals 27,466.49. The loss reduction is the difference between these two values, resulting in a reduction of approximately 37.7%. This means when we installed the capacitor bank to improve the target power factor, we got reduction in losses by 37%. This is really a cost saving and have payback period less than 6 months. Thanks for watching patiently this video. Next time I'll do another case study on a different scenario. If you want to ask a question or you have a different case about capacitor bank, feel free to comment. Please like, share and subscribe.